In this video, we're going to begin discussing line integrals, which are generalizations of typical integrals over an interval that you've seen since single variable calculus. And they're used in a variety of ways in physics and engineering applications. And so it really becomes an important concept in a lot of different contexts. So we're going to start off by developing a line integral, much like we did with integrals with single variables, integrals with multiple variables, and integrals of vector functions. So to do this, we're going to let C be a smooth curve in either the plane or in 3 space. Given by a vector function, r of t, either of the form x of t, y of t, in the case of a plane curve, or r of t equals x of t, y of t, and z of t, in the case of a space curve, where t is going to range from a to b. So those are both inclusive, including a and b, so a closed interval, which is inside the domain of a function f of xy or f of xyz, respectively, in the two cases. And so these are the two components that we need to form a line integral. We need a function, either a 2-variable function or a 3-variable function, depending on if we have a curve C in the plane or in space. And we need this curve C that is smooth and has a vector function representation. And so given this function and this curve C, we are able to make an integral out of these two things, sort of in the standard way. All right, so we're going to break up the interval a to b into n subintervals for some number n, and we want them to have equal width. Right, so we will define a to t1, t1 to t2, t2 to t3, and so on. And the last one will be t sub n minus 1 to b. So for each of these subintervals, I'm just going to represent it by t sub I minus 1 to t sub I. So represent all of the subintervals. We're going to let ds sub I be the arc length. Between r of t sub I minus 1 and r of t sub I. All right, so this would be the distance along the curve from these 2 points. And then we can form a Riemann sum. In this case, it'll be the sum I equals 1 to n, 1 for each of the subintervals. And we're going to evaluate our function f, which is a function of 2 variables or 3 variables, depending on if we're looking at a plane curve or a space curve. The input for our function is going to be r of t sub I star, which I'll define in a moment. But r of t sub I star, if we input a value into a vector function, we get either 2 or 3 components, and those are going to be our variables. And dsi, we're going to take this with respect to the arc length of that particular arc. And so the only thing I have to do is tell you what t sub I star represents, And this is just is any point that I choose from the subinterval t sub I minus 1 to t sub I. Right, so for each of those subintervals, I pick a point, I evaluate my vector function r of that, and I get a point on my curve C, and I take the coordinates of that point on the curve and evaluate my function f at that, multiplied by the appropriate arc length, and then summed together. And so we have a Riemann sum, and then the next step is to take a limit as n goes to infinity, and we get an integral. And this integral we're going to call the line integral. Right? So we can go ahead and define this. We have all of our pieces. I'm going to define it for two variables, so a function f of two variables and a curve in the plane. You can just as easily define it for a function with three variables and a curve in space in a very obvious way. And so if f of xy is defined on a smooth curve, C, given by r of t, we're going to define the line integral of f along C to be the following. So we're going to do an integral sign with a subscript of a c of our function. So the c will be our curve. It'll be ds with respect to arc length. And the definition is that the limit as n goes to infinity of this Riemann sum that I have above. Now I'll mention here, in terms of notation, this is sometimes denoted with an integral sign with sort of a circle in the middle of it here. I'm not going to use this notation, however many books do. So if you see this, this is describing the same thing that we just defined. Now, of course, like with every other type of integral that you've ever seen, we're never going to use the definition to actually evaluate the integral. And so we need to come up with a better way of writing this limit of a Riemann sum in order to actually evaluate it. So recall that when we discussed arc length earlier in the course, we defined this arc length parameter s of t to be the integral from a base point t naught to t of the integral of dx dt squared plus dy dt squared du. So we thought of that function as a function of a dummy parameter u. If we then differentiate this, we have ds dt equal to the integrand. This is just the first fundamental theorem of calculus. So we have the square root dx dt squared plus dy dt squared. And now thinking of ds dt as a differential, we see that ds is equal to this square root times dt. And so with this description, we can actually now write the line integral of f of xy over c, ds, as the integral from a to b of f of the vector function r of t that gives us the curve, ds, which is this expression that we just developed, which is dx dt squared plus dy dt squared dt, which is sometimes written shorthand as f of r of t multiplied by the magnitude of r prime of t, dt. Right, so recall that that square root is simply the magnitude of the derivative vector function. And so this here will be our approach to evaluating line integrals. Right? We take our function f, we substitute in the vector function that describes our curve, that's r of t, and then we multiply by the magnitude of the derivative of r of t. Before we look at any examples evaluating line integrals, we want to talk quickly about a couple properties that become important as we go through our study of line integrals. The first important fact is that the value of this line integral does not depend on the parameterization. Of the curve. Right. Assuming that C is sketched out exactly once from A to B. Right? And this goes back to the arc, really just the idea of arc length. In order to define the arc length integral, we need the curve to be sketched out exactly once along that interval. And so if we want to find a line integral over a particular curve C, what this tells us is that we just need to find a parameterization for it. And we can find different ones. It really doesn't matter which one we pick. The actual value at the end of the day will not be impacted by the choice of parameterization that we choose. Right, so this is actually a really useful fact that we're not going to prove here, but it's not very difficult to show using some vector calculus, but it is something we'll use from time to time. The other property that we want to make a note of now is what this integral represents. We know the standard integral of a single variable function represents the signed area under a curve. We've seen that a double integral will give us the signed volume under a surface, and so on. And in this case, we do get sort of a geometric interpretation of this. And so the line integral of f of x over c is going to represent the area of one side of what I'm going to call the fence, and I'll have a picture of this in a moment, whose base is the curve C, and the height of the fence above the point xy is the function value f of xy. And so here's the graphical interpretation of the line integral. So you can see here we have a curve C in the plane, and that's given by the black curve in the xy plane. The red curve here is the function f of xy. And the way that this fence is built is that we build the fence on the curve C, and the height is that function value of the appropriate point in the plane. And you can see that area, if the curve is above the xy axis, that area of one side of the fence is counted positively. That's the green area. And any point below the xy plane, if the surface lies below the curve C, then that area is counted negatively. So the same kind of conventions that are used for single and double integrals. And so in this case, when we think of line integrals, we're really thinking of painting the sides of fences built on our curve with a height given by our function f. So let's take a look at a quick example. So let's say we wanted to evaluate the line integral over c of the function y minus xy squared where c is the upper half of the unit circle. Right, traversed counterclockwise, which I'll abbreviate as CCW. The first thing we need to do is to find a smooth parameterization of our curve C, in this case the upper half of the unit circle. And we know that this can be done many different ways when we studied vector functions. So one of the common ways to get a counterclockwise unit circle is by taking the x-coordinate to be cosine of t and the y-coordinate to be the sine of t. If we let t to be all real numbers here, we will get the entire unit circle. So to just get the upper half, we want to restrict t to be between 0 and pi. It's not the only range that works. For example, we can go from 2 pi to 3 pi or 6 pi to 7 pi, something like this. But 0 to pi is the most obvious choice to do this. And we have our function f, and we have our curve C with a nice smooth parameterization. And so now we're ready to compute our line integral. All right, so the integral we want to compute is the integral over C of y minus xy squared ds. All right, so now we just substitute in our values. We have a definite integral here from 0 to pi. We want to compute f of r of t. So we're going to substitute cosine of t in for x and sine of t in for y. So we're going to have sine of t minus cosine t sine squared of t. Right, that's y minus xy squared. We want to multiply by the square root of the derivative, sum of the derivative squared. So the derivative of cosine t is negative sine t. So we want to take that and square it. We want to add to that the derivative of sine t, which is cosine of t squared, right, dt. Right, and so this is the formula that we derived just a moment ago with this particular function and curve plugged in. Notice that this square root is equal to 1. That's just the square root of sine squared plus cosine squared, which of course is 1. And so what we end up with here is simply the integral from 0 to pi of sine t minus cosine t sine squared t dt. And this is just a standard single variable function integral. All right, so to compute this, we're just going to find an antiderivative. So we're going to have negative cosine of t minus, and an antiderivative of this will actually be sine cubed of t over 3. If you want to do the substitution on that one, it's going to be u being sine of t and du being cosine of t dt. But that's a very, very straightforward substitution. And the antiderivative there will be sine cubed over 3. And so we'll go from 0 to pi. And so when we evaluate this, when we evaluate at pi, we get negative of negative 1, which is positive 1, minus sine of pi, which is 0. And we subtract from that the negative of cosine of 0, which is negative 1, minus 0, cosine of 0. And so this becomes 1 plus 1, which is 2. Right? So the integral of this particular function, this line integral, the function y minus xy squared over the upper half of the unit circle is 2. And so what this means is that if we would build a fence on the upper half of the unit circle, and the height of that fence was given by y minus xy squared at each point, then the signed area of that fence, one side of that fence, would be exactly 2 square units. Let's take a look at an example of a function of 3 variables. Let's say we wanted to evaluate a line integral over curve C of the function xy plus z where C is the line segment. From the point -1, 2, 5 to the point 2, 0, 1. Now, even though this is a function of 3 variables and our curve is a curve in 3 space, the approach is exactly the same. Our first step is to find a parameterization, a nice smooth parameterization of this line segment. And so in this case, we can start actually by trying to parameterize the line from between these two that contains these 2 points. And so if we do that, we know that that line will have a direction vector of 2 minus -1, comma 0 minus 2, comma 1 minus 5, which will be the vector 3, -2, -4. And so we know the whole line through these 2 points is parameterized by our starting point, -1, 2, 5, plus t times our direction vector, right, which is given as -1 plus 3t, 2 minus 2t, and 5 minus 4t. Right? So this will give us the entire line through those points. However, we only want the line segment. Now notice with this particular parameterization that when t is equal to 0, we're at our starting point. We get -1, 2, and 5. And because of how we defined our direction vector, if we take t to equal 1, we will get the point 2, 0, 1. And so the segment between these 2 points is going to be given by this parameterization by adding on the requirement that t range from 0 to 1. And so if we do that, this becomes the parameterization of our line segment, which is exactly what we wanted. So this is our line segment C. So it's the same parameterization as the line, we just restrict our domain to be between 0 and 1. And now this example is relatively straightforward. So we want to integrate this particular function with respect to arc length over curve C. Okay. And so to do that, we're going to take the integral from 0 to 1, the bounds on our parameter of our curve. We're going to substitute in the components of our vector for our vector equation for our curve in for x, y, and z. So we're going to integrate -1 plus 3t times y, which is 2 minus 2t, plus z, which is 5 minus 4t. So this is our function. And we want to multiply this by the square root of the sums of the derivatives squared. So the derivative of x with respect to t is just 3. So we'll have 3 squared there. The derivative of y with respect to t is -2. And the derivative of z with respect to t is -4. Right? And all of this is dt. And so what we end up with here is the integral 0 to 1. If you go ahead and multiply and add these things in the brackets, that's just algebra, so I'm going to assume that you can do it. But we will end up with -6t squared plus 4t plus 3. So again, that is just algebra there. And this square root is going to be the square root of 29 dt. Right, and so to find the exact value of this line integral, we're going to have the square root of 29. We'll have an antiderivative here of t cubed over -2 plus t squared over 2 plus 3t from 0 to 1. And so we have square root 29 of -1/2 plus 1/2 plus 3. And of course, evaluating everything at 0 will give us a 0. And this ends up just being 3 times the square root of 29. And this is the value of our line integral.